I'll get into it here. And so, yes, I'm going to talk about the mechanics of polymeric gels. Thank you for having me and listening. And this is a long-term kind of research topic for me. It's been about 10 years now. And, I started small and I've added on here and there as the years went through. So what you're going to be seeing today is really this culmination of many different individual topics sort of strung together. And the overall foundation is you've got a coupled deformation and diffusion behavior of a polymeric gel. And I'll show you what that is coming up soon. Really, how am I going to break this down today into a couple of different sections? I'm an engineer, so I'm going to start with some experiments, and we're going to try to probe the behavior of these materials. And hopefully in time, you'll see this is very rich behavior exhibited. So there's a lot of interesting things going on constitutively for us. Then, as my training is in continuum level constitutive mechanics, solid mechanics rather, we'll go over a continuum level model, and we're going to try to take into account three main factors: the coupled deformation and diffusion, so fluid moving around as the body deforms, inelasticity, which I think is very interesting, and anisotropy through embedded fibers. Then I'll show you some simulations where I've numerically implemented this into finite element code. And the last bullet point there is the sneakiest one. This is the yet in progress portion, is the calibration. And hopefully one day we can actually validate this model. We're not quite at validation yet. And the outline is basically follows the tasks there. So why would anybody care about this? Well, there's a couple of reasons for it, and I think some of them are pretty interesting. On the left side of the screen here, you see an example that's now 20 years old of microfluidic valves. And nothing particularly fancy these days, right? Old technology, but back then, having the valves open and close was a novel idea. And the valves that you see here are pH sensitive. So if the pH is too high, the valves would open through swelling. They would absorb the fluid and open up. And then as the pH lowered, the valves would shrink down again. The fluid would come out of the polymer material, and then the channel is open for flow once more. And these are hydrogel materials. They are very, very soft, gelatin-like, right? Very, very soft, probably 95 or more % is water, and only 5 or less % is the polymer, underlying solid. And now you transition to the right side of the slide here, and you see this is an oil well packer. And so the oil companies, when they're drilling down into the earth, they will use these rubber-like materials. And this really is like on a car tire or a motorcycle tire, a very tough rubber. And it swells in the crude oil. So if you're digging down in the earth, the picture you see down here at the bottom, this rubber is attached to the drill pipe. And if you happen to strike oil, it will slowly swell. We're talking a time scale of weeks or so. It will slowly swell to seal that off. And they don't necessarily want to have mixing of the oil with, let's say, groundwater. Right? So the range of materials goes from very, very soft to, car tire rubber. Right? So there's a large range there. And these things have applications all over the place. One of the largest consumer products is baby diapers, actually, to absorb the fluid. But there are, other more interesting applications like tunable contact lenses. the picture on the top here is for drug delivery. So you can swell this material with a particular drug, put it in a capsule, put it in the body, and then over time it will slowly diffuse the drug out. Um, a little more interesting to me, I'm not very biology oriented, so as an engineer, robotics is something a little closer to home for me. And so people are using these materials now for soft robotics. Um, the picture on top is some little swimming robot. It's not actuated by the fluid, but it's a gel material to try and give it some buoyancy so it doesn't float or sink naturally. Um, the image at the left bottom image there is a little gripper. This one happens to be electrically actuated. What you can't see is that it's submerged right now in operation. Uh, and the image to the right there is something more like just a flexible gripper. It's pneumatically driven, but this is towards where people would like to go. And I guess it's 2 years ago now, the US National Science Foundation has a program called Emerging Frontiers in Research and Innovation. And these are sort of outstanding, new, emergent future ideas, and they do two of them every other year. In 2019, they did. I don't know what this means. Chromatin and epigenetic engineering. It's probably something biological. But the other one that I've underlined here is continuum compliant and configurable soft robotics engineering. And these awards are essentially $2 million over 4 years. They have multiple universities involved, and so it's a big deal. These soft robotics, there's real money behind it, and so that's one of the things that I really care about. Why to do it? So, as an example here, a friend of mine, Ho-Wan Lee at Rutgers University, is also in New Jersey. Um, I'll play the video for you, and what you're seeing is he's constructed a polymer material here, and it's swollen. It's inside of a fluid bath right now of water, and the temperature is going to rise. Right? So what you see in this video, as the temperature goes up, the swollen polymer reduces down to its original dry shape. It's not 100% dry because it's still immersed, but the reason I like to show this video early on is because it's exactly counterintuitive to what everybody thinks at first. Most people would think if you raise the temperature, you should swell more water inside of this polymeric gel, but in reality, as you raise the temperature, you would typically deswell. Uh, so now, what are these polymeric gels? Uh, it's essentially a polymeric network. So think of a rubber-like material swollen with a fluid. Right? And that's really all there is to it. Of course, there's many varieties. And so one of the first things we tried to do in the lab was make some hydrogel, particularly a NiPAM hydrogel. And it requires chemicals and mixing. And I will tell you now, it was a complete failure for us. We could not do this repeatable, no way, no how. And so we just gave it up. And we turned to something that we found much easier. And the more easy way for us was take a rubber-like material that you purchase. So many of you may be familiar with something called VHB. It's made by 3M, and it's double-sided tape in essence. And it's an acrylic-based polymer. And this material will swell in a suitable solvent. Now, it does very little in water, right? So water is no longer a good solvent for us. And so we had some chemicals sitting around. We tried it out. And sure enough, if you take this VHB material, which is considered regular elastomeric-like material, you swell it in pentane, xylene, and toluene. And sure enough, as you see in the images here, our dog bone tensile samples on the top after sitting for 24 hours in solution, they're now swollen and they're bigger. And so this is our way of saying, how are we going to do some experiments on this material? Well, we're going to buy this VHB. To be honest, we already had it in the lab. So we used what we had. And then we just went to the people next door and said, do you have any solvent? And they said, yeah, here's a couple, try it out. And it worked. So then what we did, we took some of this virgin material, and with the virgin material, I'm going to start in the top left corner here. We just have the baseline material behavior. Right? There's 3 curves here. The blue data is the one to focus on right now. It's at a stretch rate of 10 to the minus 4 per second. So it's not fast. It's pretty slow. It's quasi-static. The stretch here goes up to more than 8. It's close to 9. And that means it's about 8 or 9 times its original length. And you could see it's showing this extensibility behavior. So at larger stretches, it stiffens up just like a rubber band would. And upon unloading, there's a little bit of hysteresis. That simply indicates we did not go slow enough to get the time-independent behavior. The 2 black curves that you see down here, they're at more moderate strain rates, and that's the data is simply zoomed in the top right image. So you've got the stress versus stretch again. And here you see the typical viscoelastic load-unload behavior. So we're going to a stretch of 2. That means the sample's now twice the length that it used to be. Loading goes up here, and unloading goes down like this. This is not plasticity, it's viscoelasticity. And we see that it's rate dependent and it behaves as a normal viscoelastomer would. To help us later on, we did a relaxation. Actually, we did a number of relaxation experiments and creep experiments to try and show that it really is a viscoelastic and it's not a permanent deformation. And using a combination of creep and relaxation, that's how we try to interpolate the time-independent behavior. So the bottom picture on the right here shows data points. Those are the experiments at what we call quasi-static rate of 10 to the minus 4. And on top of it, the blue and red individual data points are the combination of creep and relaxation. We just have to wait, a day or 2, and then at equilibrium, we get a single data point and then connect the dots, and we call that the time-independent response. So this is our baseline material behavior, and now we say, okay, we're going to swell it. Now you already know what happens. I already showed you the pictures, but here are the same pictures with a little bit more of information. The only new information is what we call the swelling stretch. And so in pentane, the body will get 1.5 times its original size. In xylene and toluene, it's about twice the original size. Right, so this is just freely swollen. In essence, take a dog bone sample like that, put it in a jar, close the lid, and come back in a while. And that's what happens. And now you say, let's do some experiments on that. So here's Nicolo's a graduate student that did a lot of this. Very careful experiments because the loads are very small and everything is done inside of a fluid bath. I have forgotten what the fluid is, but he used combinations of mineral oil, water. He played around with the fluid to stop the evaporation of the solvents. So we did not want to have, a gallon jug of toluene, sitting in the lab. So we would swell the samples in solvent and then immerse them in another fluid to stop the evaporation. So the experiments are happening inside of a fluid bath. It's just that the fluid in the bath is simply stopping the evaporation of the solvent from within the polymer itself. Oops, I went a little too quick there. So this is, to me, this is like a bang of a result. It doesn't look like much to you. It probably looks like a lot of white space, but these curves are remarkable. It's the same. It's stress versus the stretch, right? And here you see total stretch on the left, and it does not start at 1 because it's already swollen, right? So we've taken that swelling into account. The picture on the right says mechanical stretch. That's only how we prescribe the machine to move after swelling. So what's really unique here? The legend gives it away. You have 3 different deformation rates, but yet all of the data is on top of itself. What happened to the viscoelasticity, right? So here we are now that it's swollen. The viscoelasticity seems to be just gone completely. So that's in pentane. We do the same thing in xylene, and lo and behold, of course, the data is different, but the trend is identical. The viscoelasticity appears to be gone, and even more, the little red X there means the samples were breaking at a stretch that when dry, they were perfectly fine and no trouble about it. Do the same thing in toluene. Again, right? The numbers are slightly different, but the idea is the same. Different stretch rates, loading, unloading, they're all on top of each other, right? So all of the viscous effects seem to have vanished, and even more, the red X indicates the samples are breaking where they were previously intact when dry. So there's a lot of interesting behavior going on there. This was a completely surprising result to us. And this picture, I think, really sums it up. When you plot all of this together, the black data is the virgin VHB material, just dry, as received. And then the various colors are swollen in the different solvents. And this is pretty interesting. So the change in modulus is acceptable. Many people are going to think about it and agree upon that. But my goodness, the viscous effects are simply gone, right? And so the question is, my gosh, is the solvent tearing apart and killing the polymer, right? What if the solvent is essentially degrading this polymer, so there's nothing left in there? And so to try and combat that, what we did is what we call solvent cycling. We took a dry sample, we put it in the fluid, take it out, let it dry, put it back in the fluid, then take it out, let it dry. And each step was a day or two. So it's not like we dip it in for 10 seconds and take it out. You put it in for a day, let it sit, take it out for a day, let it sit, put it back in. And what we found is after 5 cycles, the material is basically unchanged, right? So when we looked at the very large deformation behavior, the virgin and samples that have been solvent cycled in the 3 solvents, it's essentially the same. And when you look at the 3 curves here, I believe this is pentane in the top right, xylene in the bottom left, and toluene in the bottom right. The data is not identically on top of itself, but this is no way close to what we've observed when swollen. So we take this to mean that the swelling, the solvent, is not deteriorating the polymer underlying polymer network. Sorry. So what we found, here's sort of the summary of all these experiments. We definitely have some inelasticity, and my goodness, how does it disappear when the solvent arrives? So that was a really interesting result. The solvent cycling tells us that there's not really any degradation or residual effect. So we take that to indicate that the swelling is reversible, right? And it's not affecting that odd inelasticity that we saw. I didn't really show numbers for it, but the one picture does show that the modulus changes. And so the very well-known Flory-Reiner model predicts the effective modulus, has this sort of trend of the dry modulus, and J is the volume ratio to the -1/3. We can measure the volume ratio. We know the dry modulus from the experiments, so our experiments show this is not the case. And as I tried to show at the beginning, many of these materials are responsive to stimuli, be it the temperature, pH, and so on. So this is what then leads us towards the model that we're going to create now. So I start with my little cartoon picture of this, what's going on in here. So if I start all the way in the top left, I've got my dry polymer network. It's tight, it's compact, and I've got these blue fluid or solvent molecules. And when they interact with each other, the arrow now goes both ways because we can swell, we can deswell. And now when swollen, what you see here is the polymer network has swollen, it's expanded, and the black lines are the same old polymer chains. They're still chemically cross-linked to each other at their junctions, right? But the fluid has simply gone inside and expanded it out. It doesn't break anything apart. There's no damage in there. And some data that we have from my buddy Hoan, that video I showed at the beginning of the dumbbell that shrinks as you increase the temperature, here's some measurements that he took. As you go from 10 up to 50-ish degrees Celsius, the swelling ratio, he's basically measuring the diameter as it changes. And so it goes, depending on the amount of crosslinker, that's a measure of the stiffness. So for different stiffness materials, but the idea here is the trend is the same. You're very swollen at a low temperature, in quotes. You hit some critical or some threshold, and then everything deswells down to sort of the dry condition. So the key features there, so the fluid migrates in, it does not destroy anything. It's going to be a reversible. The swelling and deswelling is reversible, but the material can be viscous, right? It does not have to be elastic material. The swelling and deswelling is reversible. I've not really shown it here, but I talked about the soft robotics earlier on. Most soft robotics will have embedded fibers to induce anisotropy and make deformations the way that we want them to be. So our model is going to include embedded fibers. And just for most people, when I was first taught as a graduate student, nobody was really thinking too much about mixing. You've got this fluid and this polymer network. The fluid goes inside and expands it. We didn't really talk too much about mixing back then. We just spoke about, well, clearly the volume changed. And so I just want to get it in people's minds. It's not just the volume change, there's also this mixing going on. So now comes the first slide with some equations, probably. And it's a busy slide. It's probably not the most easy to follow. So let me walk through it here. So the kinematics and important fields. So we've got three configurations that matter to us. The dry reference configuration all the way on the left here. Then all the way on the right is the deformed or the current configuration, and that's a product of swelling and mechanical deformation. The swelling, you could say, is, we had this sample, for example, we put it in a jar of toluene, close the lid, came back in a day. There, it's just the volume change, essentially, just swelling. Then we could take that sample, go over to the testing machine, go to the Instron, and do a tension test on it. So that's one of the reasons why we have this breakdown for mechanical and swelling components. Now you see some lines on here. That's because I'm trying to indicate the fibers that we're going to embed. So we're going to assume that there's multiple fiber families, and they're given by a direction A in the reference configuration, and the superscript indicates which family it is. The lines have different thicknesses because, well, some could have different volume fractions, right? Not all fibers need to have the same volume fraction. So the key points here are, for me, the deformation gradient is F, and it's broken into a mechanical and swelling component. The swelling is spherical, so it's just a scalar lambda S. That's the swelling stretch identity. We know that there's fluid going around in there, right? It's swelling, so we need to know how much fluid we have at a material point. So this CR is the concentration per unit reference volume. And a little easier in the literature, you'll find this phi. It's the polymer volume fraction. It's nice because it varies from 0 to 1. And if phi is 1, it's 100% polymer dry. And then as phi gets lower, you have more and more solvent. I already mentioned here about the fibers. They have a direction and a volume fraction. For later on, I'm going to have some internal variables. They're tensorial internal variables, and these are going to help characterize the viscous response for us. For me, Cauchy stress is a capital T and absolute temperature a capital theta. So with that in hand, I need to mention what are the assumptions here. And so I'll start with the fibers. Each fiber family has a direction A and a volume fraction. The key assumption, the fibers do not swell, right? They're simply there mechanically. And so to measure the deformation of the fibers, as is typically done in the literature, we have the pseudo invariant, right, which is the stretch squared along the fiber direction there. And that's pretty normal in the literature. She's probably gone, but Professor Naranoki, we borrowed some of her work for the anisotropy. The relative volume change due to swelling, so the determinant of the swelling deformation is given by JS there, and the kinematic assumption is that all swelling change is due to the fluid, right? That's it. So omega here is the molar volume of the solvent, CR is the concentration per reference volume. And so this is essentially saying JS minus 1 is entirely omega CR. And it's just written here as JS equals 1 plus omega CR. And so that means, in essence, if there's any fluid, it causes a swelling volume change. Now, unlike many, we are not going to enforce strict mechanical incompressibility, and the reason for that is twofold. One of them is for the numerical simulations. It's a little easier for us to have a bulk modulus, and the other one is for O-rings and things like the oil well packer. There really are some volume constraints and issues going on that people really do care about. So when we take that sort of foundation, not going to go through all the details here, but to satisfy the first and second laws of thermodynamics, we have a free energy function, and the stress and chemical potential are derived from that free energy function. Now, stress we have because, of course, I'm a solid mechanician. Chemical potential we have because that's what drives fluid flow. Right? It's not in some cases, the civil engineers like to talk about poroelasticity in soils, or the pore pressure that drives fluid flow. Here, it's more of a chemical effect, so it's the chemical potential that drives fluid flow. And this second term at the back end of the chemical potential here, this arises because of that kinematic constraint on the swelling deformation, right? And truly, because there was empty white space on this slide here for heat flux and fluid flux, we take a Fourier's relation and something similar to a Darcy type relation. In essence, that the flux is proportional to the gradient in the driving variable, either temperature gradient or chemical potential gradient for the fluid. So now we're going to start to specialize the free energy function for a polymeric gel in particular. And so the assumption is that we've got a number of things in concert. The first one being the polymer matrix itself, the second one being the fibers, and the third one being that mixing that I was talking about. And so you see all the F's sub R coming in. That's just because the fibers do not mix. And so we want to take the fibers out of the mixing. And again, we've got fibers in a matrix, and each fiber can have its own volume ratio, or a volume fraction rather. So we take the polymer matrix now, and we say to ourselves, we had some experiments earlier, and it looks like there's a time-independent portion and a time-dependent contribution. And we come to that from doing the creep and relaxation experiments, right? If we did creep and relaxation and we wait a very long time, we get some time-independent behavior in terms of stress and stretch. But then if we do load and unload at different rates, we see obviously there's some viscosity going on in there. So that's where the time-dependent comes into the picture. So for those familiar with rubber elasticity or hyperelasticity, we start with the Arruda-Boyce model. That's a non-Gaussian statistical mechanics-based model that takes into account limited extensibility or chain locking. But before we get to it, don't forget our measurements indicated that the modulus, when swollen, is not doing what Flory Riener expected. And so we're going to add something. There's a fella in Japan, Dai Okamura, had a very nice paper to try and capture that dependence. And what he does there is he adds this exponent Q. So if we were to take Q, I guess I should say what's in red color here is that modification. If we take Q equals 0, then we essentially reduce back down to the Arruda-Boyce model. By taking Q non-zero, at the end of the day, it will help us to obtain the experimentally measured, at least in a phenomenological sense. It will help us obtain the measured modulus. And so you'll see here this very last term, that's where we add on our bulk modulus, so it's not 100% incompressible. Right? So the log Jm is just the mechanical portion. And the Js is floating out front because this is a energy per reference volume. However, this term right here inside the square brackets would be after already swollen. Right? So the Js makes it per reference volume. And just like standard hyperelasticity, we have the effective stretch. 1/3 trace of C or 1/3 I1 with the square root there. Because of the kinematic decomposition of the deformation gradient into mechanical and swelling, the effective stretch has two components. One of them is mechanical and one of them is swelling. So that's rather nice. Just get my eyes on the clock. So now we're going to turn our attention to the time dependent. And from here, if I'm going to be totally honest, we started with a work by Christian Linder from 2011. Turns out it's they basically found what was already maybe not identically, but they found an idea that's been floating around for a while. And for the time dependent portion of the polymer matrix, you're looking at it's a rather simple form. And what you see here is there's a time dependent shear modulus. And it really, the energy depends on how far away an internal variable A is from the distortional mechanical C. And that's a measure of deformation. We make everything here distortional in the sense that it does not include any volume change. So we're assuming that the viscosity or viscoelastic effects are not operating on the swelling, just on changes in shape, but not changes in volume. Right? So that's what the little DIS is to indicate. It's just the change in shape, not change in volume. And we take alpha of these mechanisms could be active, and the internal variables evolve with a very simple evolution here. And so now it becomes clear that these internal variables A are always trying to be the inverse of this C mechanical distortional. Right? And the relaxation time constant is tau. So it's not a very complicated choice. but it works rather well, and that's why we use alpha of them rather than maybe a single nonlinear evolution or energy function. And for the embedded fibers, if everybody goes back to the one of the basic solid continuum mechanics books, you'll find in Holtzapfel, and we borrowed a lot of this idea from Professor Narnoki, where you've got a modulus for the fiber family, and then it's simply the I4 here. If you can remember, it's related to the stretch along the fibers, right? So it's not linear, but it's a rather simple choice for the fibers. And we're satisfied with that because in the bigger picture, the fibers are not necessarily doing large deformations. They're mostly around for the ride, you could say. They constrain motion more than drive motion. So now the last piece of the free energy is the mixing contribution. And so for this, we go to the chemical engineering or the chemistry, polymer chemistry literature. And we find the Flory-Huggins model is very popular for mixing a polymer with a fluid. And if you go to some textbooks, this is exactly what you'll find. And there's a single parameter chi that shows up. And this is called the Flory parameter, the interaction parameter, the chi parameter. And this is the thing that determines if you will swell or not, and to what degree you will swell. It's called the interaction parameter because it really shows you how well the solvent and the polymer want to mix or not mix. So as an example, if you look at the picture on the bottom right here, chi equals 0.1 is in blue, 1.0 and 2.0. So this is just a schematic essentially showing the energy of mixing versus polymer volume fraction. So 1 is a completely dry polymer. As you go towards 0, there's more and more fluid. And what I want you to notice here is just simply based upon chi, I know there's no numbers on the energy axis, but the blue is always negative, the red is always positive, right? And so a positive energy of mixing means, well, it's not really going to mix. It's like water and oil, right? They're just going to sit there separate from each other. But the blue has a negative energy of mixing, so they really do want to mix. And so they will swell together. The movie at the beginning motivates this particular choice. In all honesty, I just simply proposed this one day where the picture is shown down here in the bottom left. This interaction parameter has a low value below a threshold, smoothly transitions to a higher value above a threshold. So there's a couple parameters, but the picture really shows what we're doing here. And this is what we use to get the swelling and deswelling based on temperature. It's a chemical interaction effect. If you were curious where this comes from, myself being an engineer, we don't get into this too much, but a lot of people talk about ideal solution mixing. And there, the picture's on the bottom left here. You've got the typical schematic is a checkerboard of black and white dots, and how many configurations can you have there? And there is no interaction between the black and the white per se. Flory-Huggins does two things. It realizes that the polymer chain is actually a pretty big chain. It's not just some dots. So the polymer chain is much larger than the solvent molecules. And it also takes into account the interaction between the two. Right. So just as a general idea, that's why we chose the Flory-Huggins and not regular ideal mixing. So when you put everything together, you get some pretty remarkably large formulas for the Cauchy stress. And the good news is they all have a clear meaning and clear where they came from. The first line here in the Cauchy stress is the time-independent contribution of the polymer matrix. Right? And so what you see here in red is that parameter Q that we've added to try and eventually help us get the slope, the modulus in tension. The phi that you see here shows how the degree of swelling affects the apparent modulus. Right? Now, if we have no fluid, this reduces down, and we have no fibers, it reduces down to plain old hyperelasticity. In the case when we do have now, sorry, I'm jumping ahead of myself. In the case here, the second line is showing the time dependent. So this is the viscous contribution to the stress. It depends on that internal variable A. And in the long time limit, this goes away and it's zero. It's only in effect while the viscous is happening. And the bottom line down here is the contribution due to the fibers. So there's a time independent, a time dependent, and then the fiber contribution to the stress. The things highlighted in blue show how the fluid has an effect on the apparent modulus. And the red, again, is our addition from the 2016 Okumura work. So now it gets even bigger, my gosh, for the chemical potential, but there's good news here. The first line is pure polymer chemistry. If you had a polymer chain and a fluid, this is what you would obtain. Now we add in the polymer matrix as a real network with elasticity. So the first line you see in blue here is the volume contribution. So you see terms like log of the mechanical deformation with a bulk modulus. This is essentially pressure right here and the energy that pressure is causing. Right, so this is the volume change within the polymer network. There's also a term that's unrelated to volume change, but just distortion of the polymer network. And of course, the last one here, the fibers, right? The fibers themselves are a constraint to swelling and therefore affect the chemical potential. So this is pretty complicated. I hope the words make a little bit of sense. And now we can start putting everything together. I realize I'm going a little slow now, so I'll speed up. So what's important here is that everything has been put together. We have a diffusivity, or a mobility rather, that depends on the concentration of fluid. So the more fluid, the easier the diffusion. And when we put everything together, we end up with three governing PDEs. The balance of linear momentum is the usual form here. Divergence of the stress plus body force is zero. We don't have any inertia. And this becomes an equation for the displacement field. The balance of fluid content, if you think of it as balance of mass, the balance of fluid content basically says if you have changes in concentration at a local place, it's because fluid either came in or went out. And the balance of energy turns into the heat equation. And so this is what I'll solve using finite elements, either full finite elements or in MATLAB when it's simple enough. So now we can show some applications of the model now. So the first application here are these thermally active hydrogels, and my buddy Ho-Wan Lee at Rutgers did the experiments. What you see here are very tiny hockey pucks. The scale bar is 1 millimeter, and this vertical axis is crosslinker, right? Not exactly, but think of it as crosslinker. So it's the stiffness, and the horizontal axis is showing different temperatures. And basically the trend is as the temperature goes up, the diameter shrinks, and we're going to use this information to now solve a boundary value problem, which is really, really simple. There's no stress. Basically, it's the easiest boundary value problem you can do for one of these materials, and the entire model reduces to a single equation right here. So we ignore time, everything's equilibrium, so on and so forth. We have some estimates for the mechanical behavior. I say estimates because they're not vetted and validated. The experimental data is over here on the left for heating and cooling. The swelling ratio is just basically the diameter versus temperature. And the model now has only chi to be determined. And so we did our calibration for chi, and like, oh my goodness, this had me smiling for a week. If you remember that tangent hyperbolic form from a few slides ago, literally just cook that up and it turned out to work for some real data. So that was great, but we're not quite finished with this. Ho-Wan has sort of moved on to other things, so we don't exactly have the most repeatable mechanical data. but it gave us a little bit of faith, so we can now play some games with our finite element simulations. And to tie it back to the very beginning, so here's a microfluidic valves opening and closing based on the temperature, and they're microfluidic valves, so they're diameter is tens of microns, 20 microns or something. So time, 2 seconds and everything is over, because they're so small, the diffusion happens so fast. And so now we say, what if we start putting fibers inside, right? Let's make it a little more complicated. So the movie that you see on the left here, it goes very fast. It starts off with a dry polymer, starts to swell. The left half of this movie is for no fibers at all. The right half has fibers, and they're only oriented vertically at 10% volume fraction. And it does what you expect it to do. And then we change the temperature so it shrinks a little bit from deswelling. And the 3D does the same thing. It's essentially the same picture. Change the temperature, and it also deswells. So near equilibrium, so just for free swelling prior to the change in temperature, these are some of the results, and it's as expected. The polymer volume fraction for an isotropic material is, let's say, 0.27. That means it's about 30% polymer, 70% fluid. But when you look at the material with fibers in it, now it's 40% solid, 60% fluid. So the effect of the fibers has not only changed the shape, but that constraint also impedes how much fluid can be swollen. And a good time is now to talk about it. There's a competition between the chemical mixing and the elastic penalty to that deformation. Same idea in 3D, except not as obvious, because the third direction, it can swell in that direction as well. So Ho-Wan built one last thing for us, a soft little gripper, and here he is putting it in water. It's nothing particularly special. He took medical gauze, like if you had a cut, the medical gauze made out of cotton, he simply embedded that in this polymer prior to curing, and that's all it took to get the anisotropy in there. And so we can do our simulations, and it's doing the same thing there. So now we say to ourselves, we've got all these things going on. We can now make a soft thermally driven actuator. So we can have fibers oriented in very odd shapes, odd directions. This is a bilayer where one layer swells, one layer does not swell, and there's fibers in there. So we can envision a future where you can design these very awkwardly shaped grippers and such. Something I think is a little more important, and I know I'm a little late, I'll go faster, is calibration. And so here you're looking at quasi-static tension of the data from the very beginning, the virgin material, and then the 3 experiments swollen in different solvents, and the model calibrated to it is the red line on top. Right? So it does a decent job at picking up the change in modulus with swelling. If you notice, the scale goes from 300 to 80, right? And then when we have the uniaxial virgin material, so here we can get the hysteresis, the relaxation data, it's working. And now when fully swollen, right? So all of a sudden the viscoelasticity is gone for pentane, for xylene, and for toluene. And the model's not perfect, but it's doing a reasonable job for that. And this kind of gives it away. So the time-independent parameters are in the top block here, right? And there's nothing particularly, crazy about that. Of course, the initial shear modulus and the locking stretch are unchanged. The fluid does not change the intrinsic material itself. Q and chi help with the change in modulus and how much swelling is observed. The time independent, and here's where you really see it. So we use 3 mechanisms. When you have the virgin material, you could see it easy in the time constants, 7 seconds, 10,000 seconds, and 160 something seconds. So we have 3 clearly delineated time constants, corresponding shear moduli. But when it's swollen in these solvents, you see a whole lot of zeros showing up. And in some sense, it's essentially just killing off the viscoelasticity there. So what have we done here? So it's been about 10 years what you're looking at here, condensed down into about an hour. And so we've got a theory and a finite element that can handle inelastic deformation and transient diffusion. I think it does a pretty good job at reproducing the major features that have been seen and measured. There's still a lot more to figure out, though. I mean, it sounds so simple, but until 2 years ago, we didn't even realize that viscoelasticity simply vanished like that. There's some recent papers, and I have to thank Nicola for being the guy that did all the hard work in there.